So we'll start with the first lab on the review sessions, and we're going to talk about the word vectors. Okay, so as you all know, the word vectors are a kind of representing words for NLP tasks, and word vectors, they rely on the distributional hypothesis of word representation. All right, so you have well studied the word vectors, and now we're going to use them, or we're going to explore them and see how they work. Okay, so we'll start with the imports, and the first function here, the load vectors function, what it does, it returns a Python dictionary that maps a word, which is in a string, to a NumPy array. So here this function takes the file name, because we have in our implementation there is a word vectors for English word vectors, there are French word vectors, and it's going to parse the text and return the word vectors. So here we are going to call the function load vectors. We are going to give it the file wiki.en.vec. So these are word vectors for 12,000 words extracted from Wikipedia, and they're going to be stored in the dictionary word vectors. So in order to use the dictionary, you are going to, if you're going to access a word vector for a particular word, you are going to access it using the key. So the key is the word. Okay, it should be in small letters. I don't think there is it's case sensitive, and it's going to return here your word vector. So when we run this cell, we expect the type of the tree vector to be a NumPy array, and then we have the length of the word vector. So as we can see here, the class is a NumPy array, and the length of the vector is 300. So it's a one-dimensional Python, one-dimensional NumPy array of 300 elements. All right. So this is the word vector of tree. So maybe we can see it. Tree vector. So this is the vector for the word tree. All right. Let's comment it out. Sadly. Now, so the first function which we are going to need to implement is the function that computes the cosine between the word vector u and the word vector v. And as you know, the cosine between two vectors can be used to measure the similarity between the two vectors. So if the vectors are perpendicular to each other, then they will have the cosine value of 1, and which means that spatially they are similar. And if they are perpendicular, they'll have a cosine of 0, and that means they are independent, linearly independent. So the cosine can be used to measure the similarity between two vectors. All right. So you know how to find the cosine between two vectors. You're going to do the dot product between the vectors and then scale it by the norms of these vectors. So the cosine between two vectors is, as we said, the dot product between the two vectors is scaled by the norm of the vectors. So it's going to be np dot. So np dot computes the dot product between two vectors, and then we're going to divide it by the norm of u multiplied by the norm of v. So in order to find the norm of the vector, we're going to use the NumPy function norm, which is in the module linear algebra, linalg. So np.linalg dot norm. So that's the L2 norm of a vector. np.linalg dot norm of v, and then we're going to return the cosine. All right. Now, to check if our function working properly, we have here, we're going to compute the similarity between apple and apples, between apple and banana, and between apple and tiger. So we should expect that the similarity between apple and apples to be the highest. The similarity between apple and banana should be high, and the similarity between apple and tiger should be relatively low. So let's see if our function cosine is working. So here we're going to get the word vector of apple and the word vector of apples. We're going to get them from the dictionary. All right, let's see. Okay, so as we are expecting, the similarity between apple and apples is 0.637, and it's the highest. The similarity between apple and banana is 0.431, and the similarity between apple and tiger is 0.212. So this is very expected, which is fine. Now, given the function that we just wrote, the function that computes the similarity between the two vectors using the cosine similarity. So there are different types of measuring the similarity. We can measure the Euclidean distance, we can measure other type of metrics, but here we're going to use this function to find the nearest neighbor. So here we want to find the first nearest neighbor to the word x. So the nearest neighbor is using our similarity function. So we have the function nearest neighbor, which takes x is a string, it's the word that we need to find its nearest neighbor, and we have the word vectors, we have the dictionary, and we have exclude words. So exclude words, these are the words that we are going to exclude in our search. So we're going to do a search on the entire dictionary to find the word that is most similar to x. All right, so here we're going to returns, let's say best word, which is a string, the word whose word vector is the nearest neighbor to the word vector of x. All right, and okay, so the first step is going to do we will loop for the entire items of the word vectors, and then we'll compute the score for everyone, and then we'll take the word vector with the highest score. So for word v, so word is the string, v is the word vector in word vectors dot items. Okay, so this is how we loop for the entire keys and values of a Python dictionary, and we compute the score for this particular word. So the score is going to be the cosine between x and v, the word vector that I just found. And now if score is bigger than best score and not word in exclude words, so what we're going to do here is to find the best score is going to be the score. So the new best score is going to be the score, and the best word is the word. So what we'll do here is we will check if the score is larger than the best score we had so far, and the word is not in the excluded words. Okay, we will the score, the new best score is going to be the score that I just found, and the word is going to be the best word. So that's it. That's how I find the nearest neighbor, and let's check if the function works fine. So here what I wrote is I tried to find the nearest neighbor to the word cat in the word vectors in the dictionary that we had earlier, and we're going to exclude cat and cats. Why we exclude cat and cats? Because the most similar word to cat is cat itself, because cat itself is in the word vector, in the word vectors dictionary. And also I don't want to see cats, I want to see a different word. If here we had cat, it will return sorry. Okay, so we have a typo here. Yeah, it's cosine. The nearest neighbor of cat is cats, as expected. So that's why we exclude cats, and we'll see, or we will have a different word. Let's see what it's going to be. So it's dog, as expected, because cat and dog appear in the same context more often. So their word representation is going to be similar. All right. So for the next part, we are going to try to find the k nearest neighbors. So here we found the only nearest neighbor, and here we're going to find a k nearest neighbor to x. We're going to look for the entire word vectors dictionary as well, and we're going to return the best words that are going to score the best similarity score. Here we have X is the string that we need to find its nearest neighbors, and we have the word vectors dictionary as same as before, and then K is an integer, the number of the nearest neighbor that we're going to find. What we need to find here, the returns of the function should be a list of tuples, which is going to be the score and the word. So the score is the similarity, and the word is how similar this, the word that gives this score. All right. So there's different ways to implement the k nearest neighbors. You can just use the scikit-learn function. I'm just going to implement it here because the size of my word vectors is small. We have only 12,000 of them. I'm going to do I'm going to store all the scores of I will find the scores of all the word vectors, and then I'm going to put them in an array. I'm going to sort it, and then I'm going to pick the top k element of it. So I'm going to create a list. Let's call it scores, or let's call it word scores is a list. Okay, and now I'm going to do a for loop for every element in vectors. So for word and vector v in vectors, okay, score is going to be cosine between x and v, and I'm going to append the score and the word in the word scores. So word scores dot append the score and the word, okay. And the next step is I'm going to do a sort. So I'm going to do the k nearest, the let's call it this sorted scores are going to be sorted of word scores. So what is my scoring function? So it's going to be lambda x, it's going to be x of 0. So the key here, so the key to how I sort my word scores is going to be x of 0. So it's the score. So what this function here, this method sort, is going to do is it's going to sort the word scores based on the first element of x. All right. Now I'm going to return. Oh yeah. So we would say here reversed equals true, because the default sorting is a descending, is an ascending sorting, but I want it in a descending order. Items. Okay. It says reverse is an invalid argument for sort. Let's use a different function, dot sort, and let's check the reversed. Yeah, okay, good. And now you can see that it's working fine. So the most similar word to cat is cat, and then we have cats, then we have dog, pet, rabbit, and dogs. So the function is working fine. I returned k plus 1 because I know the first one is going to be the word itself. That's why I returned k plus 1 similar. But this you can modify it. Let's move to the next part, which is we're going to compute the analogy between word vectors. So as you know that the analogy test is one test to find it's one of the intrinsic tests in word vectors that people use to see if the word vectors algorithm learned a good relationship between the word vectors. Okay, so let's move to the slides here and I will show you. So suppose we have the word vector of a king and the word vector of man and the word vector of a woman, and we need to find the word vector that is going to give that's same distance away from king. So we can use the information of man and woman to give this information to king in order to find the word vector here, the missing word vector. So how we have king minus man plus woman equals something, and in this case you can imagine this subtraction here is like taking the manhood feature from the kingness, and then we add the remaining kingness to the woman, and then we'll find the word vector. So in this case, this word vector is going to be queen, because the king and queen should be same distance from just like the distance between man and woman. So because the word vectors are vectors in high dimensions, so the dimensions can preserve this information. So in order to do that, we are going to find we get the word vectors of C, we add to it A, and then we subtract the word vector of B. So it's a bit different in the code, but it's not a big problem. They're all normalized by the length, and then we're going to find the argmax. So we're going to find the nearest neighbor, or the k nearest neighbors of the word vector that we're going to find here, and these are going to be the word that they are analogous, the word that complete this equation. So going back to the code, let's see here, we have in the example, we have France minus Paris plus Rome equals something that we're going to find. So here we have the word A is Paris, the word B is France, and the word C is Rome, and we need to find the word D. So we're going to use this formula to find the word D. Okay, so it makes sense because D should give us the fact that A to B equals or similar to C to D. So the word vector that we're going to find, we will get it using the equation we used before, and it should be, remember, it should be normalized. So we should divide the word vector by the length of the word vector, by the norm of that word vector, and then we'll use the same formula we've seen before to find the word vector, and then we'll get the nearest neighbor to this vector. So we're going to find the word vectors that has the highest cosine similarity of the outcome of the equation. So here what we'll do is first we'll get the word vector of A, so VA equals word vectors of A, VB equals word vectors of B, VC equals word vectors of C, and then we're going to divide each one by its norm. So VA equals VA divided by MP.linL dot norm of VA. We'll do the same for VB. I'm gonna copy it to save some time. VP equals VP divided by VP. VC equals VC divided by the norm of VC. Now we're going to return the nearest neighbor to the vector, nearest neighbor for VC plus VB minus VA, and we'll also pass the word vectors, which we are going to search on vectors, and we are going to exclude A, B, and C because the word vector could be similar to A or B. So we are going to exclude them. So we want the nearest neighbor in the dataset that is not in A, B, C. So we just translated this formula here into code. Right? So we have VC plus VP minus VA. Each one is scaled by its norm. And then we'll find D. So we'll find the nearest neighbor to D that is not C or B or A. Okay. So if we're going to complete this equation, let's see what's going to be the result. So surprisingly, or not surprisingly, the most analogous word is Italy. So France to Paris is like Italy to Rome, or Paris to France is like Rome to Italy. Okay, so let's move to the next part. Here we're going to understand the bias in word vectors. So we should be careful that when using the word vectors themselves will reflect the bias that we have in our dataset. Suppose we have a dataset where the word genius the word genius and man come together more frequently than word genius and woman. So in the representation, when we find it, the similarity between man and genius will be much higher than similarity between woman and genius. And let's see that if that's the case in our dataset. And unfortunately, that's the case. So the word vector of man is more similar to the word vector of genius compared to the word vector of woman and genius. So now, to test the bias in the word vectors, so the different ways to do that, but here we're going to use the association strength. So we're going to measure some form of association strength between, we have a word W and sets of attributes A and B. Okay? For example, suppose we have the word man, and then we have attributes like, let's say, a set of attributes that contain information about career. Let's say salary, office, management, profession. And then we have a different set like home, like parents, like children, like food. And so if our word is man, then we'll see if man is more associated to one set or the other. So that's what we're going to find here, and we can go to the slides to see what's the mathematical formula that people use to compute the association strength. So let's go to slide 91. So here, to measure the strengths of association of a set of words, suppose we have a word W and we have a set of features A and a set of features B, and we need to see if there is an association or there's a difference in not a difference, but yes, it could be a difference in if between the association of the word W to the set A or set B. So if the words in set A and set B have, let's say, on average the same distance from W, then we have a value of 0. But if there is a difference between the two sets with respect to W, we'll have a value that's not 0. So here in this case, what we're going to do is to compute the average cosine similarity between the word W and all the word vectors in set A, and we're going to subtract from that the cosine similarity between the word W and all the words in set B, and subtract the two values from each other, and then we'll see. So if the value is 0, then the word W is let's say the same is the same distance away from the words, from the average of the words in set A and the average of words in set B. But if the word is similar to one of the to one of the sets, then we'll have a value that's not 0. Okay, so it can act as a kind of a measure to the similarity between the sets with respect to the word W. So we can use it to look at the bias. If a set of attributes are biased towards a word, then we can use the value here to tell us how biased these set of attributes with respect to the word W. And now we can also generalize this concept to having a set of words. So here we used one word, but here we have two different sets. So suppose we have a set of word vectors, and then we have two sets of word vectors, and then we have two sets of attributes. If the sets of these words are similar with respect to the attributes, we'll have values that's 0. But if there's a difference if there is discrepancy between the two sets, then we have a value that's not 0. So S here is just this association strength. So we're going to compute the association strength for each word in X with respect to the sets A and B, and then we'll also compute the association strength of every word in Z with respect to the set of features A and B, and the value that we're going to get in the end will tell us how much different these two sets with respect to the features. So every W here is a word vector, A is also a word vector, so the feature itself is just a word, but its meaning is different, as we're going to see in the example. But that's how I compute the association strength between a word vector and the set, and between two sets. As you can see, the formula is very straightforward. We're just going to do a for loop, and we're going to compute the cosine, then we'll take the average. So we'll do it directly here. So move to implement it. So here we're going to do a for loop for A, let's say AB in zip AB. So the zip function will make us put two collections together, and then we're going to loop for them. But I don't think using it is right, because A and B should be the same size. Let's just do a normal for loop for A in A, strength plus equals cosine of the vector, the word vector of W. So here we have W is the word vector that I need to find the strength for, and A is the list of strings. So these are the words that belong to set A. B are the list of the vector that belong to set V, and vector is the word vector dictionary that we used before. So here we're going to complete the function. We need to complete the cosine between vector W and vector and the word vector of A, and we're going to divide by the length of A. Okay, this set A. Now for B in B, strength minus equal cosine vector of W and the vector B, and we're going to divide by length of B. So this is just translating the formula as it is. Here I'm going to compute the lengths every single time, which is expensive, so we can do strength actually I cannot do it now because because if I divide by the length of b here, then did you see what I'm done here? I couldn't divide by the length of b outside because I will divide the entire strength variable. It's vectors. Yeah, sorry. If it's confusing, let's call this part. Let's call it this part A, and then we'll divide part A by part A, and then we'll call this part B, part B divided by length of B, and then we have strength equals part A minus part B, but here we have a summation. Now it's obvious. Let's look at the formula and compare if it's the same. So we collect the cosine similarities for part A. So we're going to do here, and then we'll divide by the cardinality of the set. Then we'll collect these similarities of the set B. Okay? And then we'll divide by the cardinality, and then we'll subtract part A, all of it. We'll subtract part B from part A, and then we'll return the strength. Alright? And now for the second function, we're just going to use the function that we used here, because here we compute the association strengths of a word to the features, and now we have two sets. So we're going to use this function to do it. Okay, now let's write the other function. So here what we're going to try to find is the association between two sets, or more clearly we're going to see if the two sets are there's a discrepancy between them given some list of attributes. Okay, so here we have x is the list of strings, we have the list of words belong to set X, and then we have Y, where it's a list of strings that belong to set Y, and then we have A and B. So we have also a list of strings, but A and B represent some attributes. So here what we need to find is if X and Y are similar or not, if we have some attributes. So also we're looking at the bias, we could be looking at the bias if X and Y are different given some attributes and A and B, then there's a bias between them. So we're going to compute the score. So for we're going to look for every word in X and for every word in Y, just like the formula here. Okay, so we can do part A initialized with 0. So for X in X, score let's say part part A plus equals the association I didn't run the function, the association strength of the word X, and then A and B, and we have the vectors. And then we can do for Y in Y, let's initialize part B, B equals 0, part B plus equals association strength of Y, A, B, and vectors. And finally the score is going to be part A minus part B. Now let's see if if we made any mistake. Okay, so now let's explain what we just did. So here we have male names: John, Paul, Mike, Kevin, Steve, Greg, Jeff, and Bill. And then we have female names: Amy, Joanne, Lisa, Sarah, Diana, Kate, Anne, and Donna. So these are the sets that we're going to find if there is a difference between them given some attributes. So the attributes here, we have two different set of attributes. So we have career attributes that are about career and profession. So we have executive, management, professional, corporation, salary, office, business, and career. And then we have family attributes: home, parents, children, family, cousin, marriage, and wedding. So if males are more associated to careers than family, and then females are more associated to family than careers, then there's going to be a discrepancy between male and female. There's going to be a large difference between the two groups. So that's one test to see if our data set, the word vectors that reflect our data set, they have some bias in them. So now, because the male names have large association with the career words, and they don't have a large association with the family, and because the females have a large association with the family and not the career, there is a big difference between the two groups. So this is what we just did. We checked if there's a difference for each word with respect to the attributes of the two groups. This is what we've done here, and then we did this for all the words inside, for both the male names and the female names, and the value is 5. So that's a large value, which means that actually the word vectors of male here are similar to or there is a difference. Of course, the number that we see here doesn't tell us which group is more similar to which group, but it just tells us there is a difference between them, and then we need to look deeper to see which group is more similar to which group. Okay, so that's how you can use it to detect the bias in your. Okay, so maybe I had something wrong. Okay, let's see. Oh yeah. Okay, now it makes sense. Okay, so now the value is smaller, it's 0.8. Maybe if we can, no. Now I did something here, just to show you. So I added the word nurse. So before adding the word nurse, the association test gives the value 0.847. But after I add the word nurse, if you look here, the value increased. So it means that now the difference is more, because nurse is more associated with female than to male. So the difference between the two groups is bigger. But let's try here adding football. Maybe if football is more associated to males. Okay, so also the discrepancy increased because football is more relative to men than. So now we can see there's clear bias in our data set. Okay, so this notebook is introduction to word vectors. It gives you an idea what are the word vectors, how do they operate, when they're useful or not. So